Welcome back. Let's continue with our lectures on mathematical method. Hope you had a good break and come with a fresh energy. We are going to start on ordinary differential equation. To begin with shortly for first order differential equation and then go on to study second order differential equation. Differential equation. This is a part of a course PH3103 at IISER Calcutta. Let's start with the first order ordinary differential equation. The general form of the first order ordinary differential equation is given as a dy by dx is equal to f of x into y. F of x into y is an arbitrary function of x and y. Usually the canonical form which we are used to is written as p of xy into dx, q of xy into dy is equal to 0. So this is a form we are generally encounter, and let's look at some of the method how to solve this ordinary differential equation. One of the easiest method to solve this differential equation is to write this as an exact differential. That is, we write it as a p into dx plus q into dy as a d of some function phi of xy. Here the solution is phi of xy is equal to constant, and which can be written as a y is equal to f of x. In general, writing explicitly y of x may be not possible. However, we know that the solution in this case is given as a phi of xy is equal to constant. The condition able to write it as exact differential is that we write p dx plus q dy as d phi by dx into dx, d phi by dy into dy for some phi. Now here we have to identify d phi by dx as a px and d phi by dy as a q of xy. Once we do that, we can impose the condition for exact differential, and that can be written as dp by dy is equal to dq by dx, which is same as writing in the form of d square phi by dx dy equal to d square phi by dy dx. So once we do that, we solve this equation d of phi xy 0, and then we obtain the solution phi is equal to constant. Let's look at a quick example. Let's try to solve an equation of the form 1 plus cos y minus cos xy into dy minus cos x plus y dx is equal to 0. So this is the equation which we have to solve. This is already in the form of p of xy plus q of xy. So we identify this q of xy as a 1 plus cos y minus cos x plus y, and here we have p of xy is equal to minus cos x plus y. Now let's check whether this satisfies the condition for exactness, that is dq by dx we compute, and it is easy to show that is sin x plus y. So we take this, differentiate with respect to x, then we find that this is 0, this is 0, and this comes minus sin x plus y, which is written as simply sin x plus y. Same way, we find that d phi by dy is equal to sin x plus y. It is trivial from differentiating this with respect to y. So we see that the dq by dx is equal to dp by dy. So it satisfies the condition required for the exact differentiation, and we can simply find phi. So we first solve for phi using the d phi by dx equation, that is p is equal to d phi by dx, that is the identification which we are doing, which is equal to minus cos x plus y. Once we can simply integrate this, and we find that the phi of xy is equal to minus sin x plus y plus an arbitrary function f of y. We need to find out f of y using the second condition, that is q of xy is equal to d phi by dy, and this equation which we have is a 1 plus cos y minus cos x plus y, and that is equal to d phi by dy. We can integrate this, and we obtain phi of xy is equal to minus x plus y, that is coming from this term, and then we have a sine of y that is coming from this term, and then we have a simply y which is coming from integrating 1, and then we have to add an arbitrary function g of x. Now we can compare these two solutions and then constrain g of x and f of y, and we find that g of x should be 0 and f of y must be equal to sine y plus y. Once we have this, we have phi of xy is equal to minus sine x plus y sine y plus y, and the solution is represented by phi of xy is equal to constant, or minus sine x plus y plus sine y plus y is equal to constant. Here we will note that it is non-trivial to write y as a function of x. Go on, another important method is an integrating factor. Now we have seen that our method of solving the differential equation essentially rely on the fact that the p dx plus q dy equal to 0 is satisfies the exact differential. That now what if dp by dy is not equal to dq by dx, that is, it does not satisfy the exact differential? Can we somewhere write down this as an exact differential? The answer is yes, and that is by using the integrating factor. We can multiply a suitable integrating factor lambda x and y such that the p dx lambda p dx plus q dy is equal to 0 is exact. So the lambda is a common multiplicative factor which we determine such that the differential is an exact differential. We need to find lambda such that the d by dy of lambda into p is equal to d by dx lambda into q, such that the differential becomes an exact differential. And now important thing to notice is that there is always a solution for lambda x y, but there is no general techniques to determine how to find it. This is an interesting place where physicists contribute by finding out unusual means to solve the problems. Let's see how to find the integrating factor. Let's first start with the first order linear differential equation. A linear differential equation is of the form p of x dy by dx is equal to q of x into y is equal to f of x. So you note that in this case we don't have a power of y more than 1, that is why it is a linear equation first order, because we have only a term of dy by dx, and f of x is a source term, or this is an inhomogeneous differential equation. Again we write this by adjusting these terms in terms of dy by dx plus g of x into y is equal to h of x. This is a more convenient form than the p dx into q dy in this case. That's why we write, because the way of finding the integrating factor is easily determined by this form. Now let's multiply alpha on the both sides. The alpha is an integrating factor such that this differential becomes an exact differential. So we multiply by alpha on both sides. The equation becomes alpha into dy by dx plus alpha into g into y is equal to alpha into h of x. Now let's say that alpha satisfies the condition that the d alpha by dx is equal to alpha into g of x, such that this can be written as a d alpha by dx. That is the main trick, so that this is made an exact differential equation. This condition essentially says that alpha should be of the form alpha is equal to e power integral x g x prime into dx. So it's easy to see or solve this equation from here to get this solution for the first order differential equation. We can simply integrate it on the both sides by rearranging d alpha and dx. Let's show that with this multiplication, the differential equation becomes an exact differential equation. We start with the d by dx of alpha into y. We use a chain rule, alpha into dy by dx plus d alpha by dx into y. Now we take this term. Now let's substitute d alpha by dx from these constraints which we have obtained, and once we substitute that, we obtain that alpha into dy by dx plus alpha into g of y. So this simply substitute this and we obtain this. Now the next step is to simplify, pull out the alpha, and then we get dy by dx plus g into y, and our differential equation which satisfies is a dy by dx plus g into y is equal to h of x, and we substitute this for h of x. That what we have is alpha into h. Now we see that d by dx of alpha into y is equal to alpha into h of x. This is the equation which we can easily integrate, so that we have alpha into y is equal to integral till x alpha x prime into h of x prime into dx prime. This being a simple first order differential, we can integrate this by taking the integral, and then we see that we have obtained the solution in terms of the integrating factor. Integrating factor in this case alpha is integral g of x prime and dx prime taken at let's take a quick example. Let's solve a differential equation. Dy by dx is equal to 1 by x into y is equal to sin x. So first we have to find the integrating factor. For that we need a g of xy. In this case it is simply 1 by x. The integrating factor which we know is alpha is equal to e power integral g of x prime dx prime. This is a e power integral d x prime by x prime, which can be integrated simply to be e power log x, and it turns out to be simply x. Once we have a integrating factor, we multiply our original differential equation with the integrating factor on both sides and try to write it as an exact differential equation and integrate it out. So we have x into dy by dx plus 1 by x into y is equal to x sin x. After multiplying and simplifying with the integrating factor, we have a x dy by dx plus y is equal to, that is x into sin x. Since this is an exact differential, we can write it as d by dx of x into y, and then we can simply integrate it over. This is a simple differential which we can integrate. We have x into y is equal to integral x prime sin x prime dx prime. You can integrate this function. This is rather trivial elementary calculus exercise in the integration, and it turns out to be minus x cos x plus sin x plus c, where c is a constant. So finally we can write, because this is a first order linear differential equation, we can simply write it y as a function of x, and y turns out to be minus cos x into 1 by x into sin x plus c divided by x. So this is a solution for the differential equation which we have started.